I am Professor Suparna Mukherjee from the Environmental Science and Engineering Department. Today I will be covering water treatment processes in the ES 200 course. So today I will be talking about the water treatment processes. So these are processes that are used for treating the water, that is either surface water or groundwater, and bringing it up to the drinking water quality standards. So we may take water from rivers, lakes or reservoirs, but as you know, the water in rivers, lakes, etc. may have turbidity and color associated with it, and it may also have other objectionable substances such as anions, heavy metals, etc. We can also take groundwater from the aquifers and treat it. Groundwater often has problems like high levels of arsenic or high levels of nitrate and fluoride that you know are associated with diseases such as blue baby syndrome or dental or skeletal decay. Sometimes there are leachates generated from dumping grounds and unlined pits that can actually contaminate groundwater even with organic substances. So this way we can take water from natural sources and try to treat it. The concern about water from these sources is that there may be pathogens in there apart from the turbidity. So for pathogens, what we can do is, these are the disease causing microorganisms in the water, which primarily reside in the intestine of warm blooded animals, and water gets contaminated with pathogen when there is contamination of the water with sewage. So under such circumstances, the water may contain microorganisms which have disease causing potential. Now we have to treat the water that we draw from natural sources up to the drinking water quality standards. It's very important that we choose a good quality source water when we are trying to select the appropriate source for drinking water. So CPCB, that is the Central Pollution Control Board, has classified different streams into A, B, C, D, E, etc. A is the best quality. For quality A, the water can be directly used after disinfection, whereas for quality C, it would need other treatment before disinfection. So quality A water is typically having high DO level above 6 milligram per liter. Coliform counts is also low, less than 50 per 100 ml, and BOD value is typically less than 2 milligram per liter. Those are the limits for the quality A water. Now as I said, we have to treat it up to the drinking water quality standards. These standards are specified by various agencies like ICMR, which is the Indian Council of Medical Research, or the Bureau of Indian Standards, or other agencies like WHO, US EPA, etc. They can also specify standards. In India, we typically try to aim the BIS standards. Now this is showing the conventional water treatment processes. So the water we take up is first screened, and then it is subjected to processes like coagulation, flocculation, settling, and subsequently sand filtration, disinfection, and then this is treated water that is distributed for our use. So primarily screening is for removing the large floating suspended objects. Coagulation removes colloids and also some natural organic matter and macromolecules. Flocculation is the process of floc formation, that is, after the colloids are destabilized, they form flocs in the process of flocculation. And subsequently there is a settling tank in which the flocs are settled out by gravity, and as a result sludge is generated. So I will not be talking about sludge processing today, but that also is an important aspect. And subsequently we have the filtration process for removal of turbidity or suspended solids from water, and the disinfection process is specifically targeting the removal of pathogens. Now, some removal of pathogens also happens in the coagulation, flocculation and filtration process. Although they are not designed to remove pathogens, they also remove some of the microorganisms like protozoan cysts, etc. Now, sometimes in addition to these traditional processes, we may also need processes which is for specific contaminants that are there in water. These additional processes may be chemical precipitation or ultrafiltration, chemical oxidation, adsorption, reverse osmosis or other membrane processes like electrodialysis, ion exchange, and I have also shown the typical placement of these additional treatment processes. These will, however, be covered in a separate lecture. I will not be talking about these today. Now, let us look at the process of coagulation flocculation in greater detail. This is the process for removal of colloids and color causing macromolecules from water. Primarily, it is a chemical process where some chemicals are added to destabilize the colloids. So, we add the chemicals and mix rapidly so that the active species gets generated and it destabilizes the colloids. The next process is flocculation, which is a process of physical contact that brings the flocks close together so that the flocks can grow in size and then they can have sufficiently large size so that they can settle out properly. Now, colloids in water typically range in size from 1 nanometer to 1 micron. Because of their very tiny size, they have a very large surface area to volume ratio. Apart from this, you also have color causing macromolecules which are removed by the process of coagulation. So, some examples of colloid is clay, bacteria, viruses and proteins. So, typically bacteria, viruses and even clay carry negative charge. Because of their negative surface charge and because the surface to volume ratio is so high, they tend to repel each other very strongly such that they cannot come together and form bigger particles so that they can aggregate and settle. So, what I am trying to show in this figure is that around the colloidal particle which is charged, here I have shown a colloidal particles that are negatively charged. They are surrounded by a zone of counter ions. This is called the electric double layer. So, there is one layer which is very high in counter ions, very close to the particle surface, and the diffused Gouy-Chapman layer beyond that. So, when two particles try to interact with each other and carry similar charge, their diffuse double layer will repel each other. They will not allow it to come close together, and that is why they cannot grow in size. So, because of this, there is a repulsion potential as shown here. The repulsion potential is caused by the specific distribution of the ions in the water in the vicinity of the charged particles. So, you see at the closest to the particle surface is the Stern layer, beyond that is the Gouy-Chapman layer, and the potential drops gradually from the particle surface to distance away from the particle surface. So, in the bulk there is no excess of counter ions over co-ions, but close to the particle surface we have excess of counter ions. That means if my primary particle is negatively charged, I will have excess of positive charge over the negative charge in the solution. So, this is the double layer, and this prevents the colloidal particles from coming close together. So, how do we overcome this? We can add coagulants. As I said, coagulants are basically chemicals which allow us to achieve the process of coagulation or the process of destabilization. So, the best example would be alum, aluminum sulfate or ferric chloride, ferrous sulfate, polyelectrolytes, etc. Sometimes we add polyelectrolyte in combination with alum and other salts. So the mechanism of coagulation can happen through multiple mechanisms. So coagulation with alum, for example, can happen through charge neutralization, because aluminum, when it dissolves in water, forms species like Al3+, AlOH2+, etc. These positively charged species will adsorb onto the particle surface which has negative charge, and that way it will neutralize the particle surface charge. So this is one mechanism. It can also cause formation of aluminum hydroxide precipitate, and as the precipitate is generated, it takes the colloids with it and settles down. This is referred as sweep flock or enmeshment in a precipitate. We can also have other mechanisms like double layer compression, that is by adding a high concentration of salt which has no other mechanism of action like NaCl, that would be an indifferent electrolyte. Okay, so this way we can facilitate the destabilization of colloids. When we are using polyelectrolytes, a bridging phenomena happens that brings particles close together to form flocks. So coagulants such as alum, as I said, can act by more than one mechanism, and this is dependent upon the solution conditions like pH, alkalinity, concentration of the colloidal substances and other things. So this is showing a typical jar test apparatus in which coagulation flocculation is done. So you see there are multiple jars, and in each jar I would add a different concentration or dose of the coagulant and rapidly mix it to generate the active species that will then interact with the colloids in solution and destabilize. So after a rapid mix period for about a minute at a high RPM, I would reduce the speed and give contact opportunities to the destabilized colloid for about 20 to 30 minutes at a reduced speed of around 25 to 35 RPM, and beyond that I will stop the stirring, and for about 1 hour I would let it settle. This is a jar test, and at the end of the jar test I would measure the change in turbidity that happens as a result of coagulation, flocculation and settling. So you see here, it is very important, the dose of coagulant is very important. So it decreases, as you increase the coagulant dose, you have more turbidity reduction. However, there is also a possibility that there can be a charge reversal. The charge reversal can give rise to a turbidity increase again. Ideally, we would like to know what is the lowest dose at which I can get the turbidity removal. However, I should also be aware of the dose beyond which I can get charge reversal. So if charge reversal happens, primary particles which were negatively charged would then become positively charged and again repel each other, right? So then I won't have good removal of turbidity. So this is what is shown in the blue line there. So what happens is, in the lower figure you see how a turbid suspension after addition of coagulant is forming flocks, and then the flocks are settling out and I am getting clear water above. So this is what we achieve in the process of coagulation, flocculation and settling. So now let's reiterate what is flocculation. It is basically the aggregation of the destabilized colloids to form flocks. Here the important thing is the rate of aggregation of the destabilized colloids. So basically the rate at which the collision between particles is happening and the effectiveness of the collision in causing attachment. Okay. So mechanism of interparticle contact can be simple Brownian motion which will happen spontaneously, or it can be a bulk fluid movement induced by stirring, or it can be due to the settling of particles. Now due to all of these interparticle contact, particles are coming together and forming flocks and increasing in size. Now we distinguish two types of flocculation. One is the perikinetic, which is the do nothing. So intrinsic property of the system, there will be some flocculation happening. And the other is the orthokinetic flocculation, where we are providing a velocity gradient in the solution, and the mean velocity gradient determines the effectiveness of contact. Velocity gradient is basically the spatial changes in velocity, and it is affected by the power input into the system. So this mean G bar value, it determines the effectiveness of flocculation, but there is an optimal range. It has to lie between 10 to 100 centimeter inverse, 10 to 100 second inverse. And the retention time for which flocculation is typically carried out is of the order of 20 to 60 minutes. And this product of G bar times T determines the mass of floc that is formed. Now flocculation is typically achieved either in a system with paddles where gentle agitation is provided to facilitate contact, or in a system where there is a long path length and that promotes contact between particles in a baffled flocculator. Now let's come to settling of particles. Now our interest here is the settling of the flocs, but let me start from settling of discrete particles. So settling of discrete particles, as you know, follows Stokes law. Okay? So the Vt, which is the terminal settling velocity, follows Stokes law and settles as per that. And we can have settling tanks either in rectangular settling tank or circular cross section settling tank. Once when we are trying to perform settling in a settling tank, suppose the particle that is entering at the top of the settling tank, that has to hit the bottom, that is the sludge zone, within the detention time. That is the important design criteria. So Td is the detention time needed. That is essentially determined by my system, right? Volume by flow rate gives me the V by Q, gives me detention time. And in this case, when I substitute for a rectangular system, length into width into depth divided by Q is my Td, and eventually I can write that as d by Vt, where d is the depth and Vt is the terminal settling velocity. So Vt, if I rearrange, it comes out that Vt is equal to Q by As, where As is the surface area of the tank. So the particles, particle settling is significantly affected by the surface area. Okay? It is determined by the surface area of the tank. So one has to ensure that settling tank is designed with appropriate surface area so as to get the desired settling. Okay? So for discrete particles, this Vt, or the terminal settling velocity, is a function of the particle diameter dp. In fact, it is proportional to dp square as per Stokes law. Okay? But Stokes law is applicable for discrete particles. Here we are talking about particles that are not discrete particles, right? These are flocs. The flocs will grow in size over time. So for the flocs, the settling will happen faster than discrete settling for the particles for same size. If I start with discrete particle and floc of some size at the top of the tank, by the time they are hitting, the flocculent particle is of a larger size. So that would have a better settling, a faster settling compared to the discrete particle. So this is referred as class 2 settling. The settling of flocs is referred as class 2 settling behavior. Discrete particle settling is class 1 settling. So basically in this class of settling, that is class 2, the particles will coalesce and flocculate during the sedimentation process. Hence the mass will increase and particles will progressively settle faster because of the mass increase. So in this type of a system, we can't apply Stokes' law. Settling efficiency will have to be determined through empirical testing in settling columns. And the extent of settling and the contact opportunities, etc., that is there will be extent of flocculation is going to be a function of the contact opportunities, the overflow rate, the depth, velocity gradient, particle concentration, and also the size of particles. So that means the opportunity for growth in size that happens for the flocks is a function of many different parameters, as we saw here. Okay, now let's go on to the next process after coagulation, flocculation, settling. This process is referred as filtration. And in most urban water treatment plants, the type of filters that we find is deep bed rapid sand filters. So basically it consists of a sand bed through which the water is passed. So whatever turbidity that did not get removed through the coagulation, flocculation and settling process is being targeted for removal in the filtration process. So we are trying to remove the flocks that did not settle out through the process of filtration. So the water is passing through a bed of sand that is above a layer of gravel, and we are trying to aim for removal of particulates such that there is decrease in turbidity. After the filtration, I want turbidity of around 0.5 NTU or less, that is good quality treated water free of turbidity. So the primary mechanism of filtration in this rapid sand filter is a physicochemical filtration mechanism. So here particle removal is happening by physicochemical forces between the particles, and there is contact between the particulates and the filter grains. Filter grains are referred as media or collector grains, C. So dC by dP ratio in this type of filter is around 1000. So the particles are of very small size, and the objective is not straining through this media, through this sand bed, rather it is physicochemical filtration that aims for the removal of particles through the filter bed. So there is little decrease in permeability if we can achieve physicochemical filtration, whereas if we had cake filtration or straining filtration, that would occur if the dC by dP ratio was much smaller. That is undesirable because that causes huge head loss development in the filter. So this is showing a typical filter with typical dimensions. So what you see is there is a bed of gravels on which there is a bed of sand, and below that there is an under drain system with perforated pipes in which the treated water is getting collected. Above the sand is a standing height of water column, and so basically the water is getting filtered and the treated water is subsequently collected in the perforated pipes in the system of under drains. Now in this type of a filter, the grain size of sand is typically of the order of 0.45 millimeter. If it is very fine, that can create a problem because it will lower the dC by dP ratio. The uniformity coefficient should be around, should be less than 1.5, okay. And so this filter media, which is a bed of sand, also called the collector grains. The collector grain size is very important in the process of filtration. So the effective size is the D10 size. This is the size of grains in millimeter such that 10% of the particles are smaller. D60 size is a size in millimeter such that 60% of the particles are smaller than this size. And uniformity coefficient is defined as D60 by D10. And as I said, that should typically desirable value is less than 1.5. So the sand grain size ranges from 0.45 to the sand grain height, The height of the sand bed is around 0.45 to 0.76 meters, and it is supported on a bed of gravel about 0.45 meters. And the D10 size of the sand, which is the effective size, ranges from 0.45 to 0.7 millimeter. Uniformity coefficient range is in the range of 1.2 to 1.75, and the flow rate is 2.4 to 34 meters per hour. The high end is for special type of filters. Mostly it's in the range of 2.4 to 5 or so. 34 and all is for typically multimedia filters. So they can be operated in gravity filter mode or pressure filter mode. More commonly we operate it in gravity filter mode, and the filter is cleaned by backwashing. So what happens is, as the filtration of water is happening, the particulates are getting deposited and the deposits build up, and with the build up of deposits the porosity decreases and the permeability also decreases. As a result of this, head loss increases and the flow decreases if the hydraulic head is constant. So there is shear stress on the particles that are already deposited, and as we continue in this way, the water quality will deteriorate over time. So it is desirable at this point to backwash the filter. So by backwashing, we mean we reverse the flow through the filter bed. Through the hydraulic action, the hydraulic shear that happens, it dislodges the particles that were attached. Okay, there is a surface scarring action also. Typically, the flow rate for backwashing is much higher than the operational flow rate. It's in the range of 36 to 48 meters per hour. Time of backwashing is small, it's 3 to 15 minutes or so, and the filter runtime is 12 hours. So you see, it's a small fraction of the filter runtime, and the backwash volume is around 2 to 5% of the filtered water. And when the backwashing is happening, the filter bed expands. There is about a 20 to 50% expansion of the bed. So after the backwashing, when it is stopped, when the flow in the reverse direction is stopped, particles will settle down by gravity, and as a result we will see finer sand grains settling on the top and the coarser sand grains on the bottom. This is actually an undesirable distribution, because in the top layers we can have straining mechanism happening, and that can give to higher head loss in the top layers of the filter. Because of this, sometimes it is there is advantage in using dual media filters, where we use another material of a lower density above the sand, and the grain size is kept larger than that of sand. So this way we can overcome that head loss development which we were talking about, which happens due to the arrangement of the sand grains as a result of backwashing. So this type of dual media or multimedia filters are shown here: coal above sand, or using coconut shell or bitumen above sand. This sort of material can be used to enhance the filtration rate through the filter. These are referred as dual media filters. Another type of filtration is possible for sand filters. These are referred as slow sand filters. Now typically the slow refers to flow rate. The flow rate is much lower. You saw the flow rate earlier for the rapid sand filter. Here it is 0.1 to 0.3 meters per hour, much less than that of rapid sand filter. So what happens here is the grain size is much finer. It's of the order of 0.2 millimeter as opposed to 0.45 or so millimeter for the rapid sand filter, and the bed depth is also much more. Okay, because of these characteristics, bed depth is of the order of a meter or so, 0.9 to 1.5 meter. Because of this type of filter design, it produces good quality water, but it will require a large land area to treat the same flow rate through the system. It will need a much larger surface area. and that can only be possible in peri-urban or rural areas. It's difficult in urban regions. So slow sand filters, although they can produce good quality water, they are not used so much. So the solids removal happens most in the uppermost layer, referred as Smoosh-Dekki, and this Smoosh-Dekki also has biological activity. So it can give very good water quality, not only because of the biological activity in the Smoosh-Dekki, but also because of the depth of the filter being much more than for the rapid sand filter. However, the flow rate is much lower, so land area requirement is much higher. Here there is no backwashing, but the top layers of the filter has to be scraped off periodically at intervals of 1 to 6 months or so. Now I will come and talk about the disinfection of water. So most commonly disinfection of water is done using chlorine. However, we can also have alternative disinfectants for killing pathogens like sodium hypochlorite. Ozone is also used, and UV radiation can also be used, but chlorine is widely used in water treatment plants, so I will primarily focus on chlorine. So chlorine dissolved in water produces HOCl and H plus and Cl minus. This HOCl can dissociate to produce H plus and OCl minus. So the two species that are responsible for disinfection using chlorine is HOCl and OCl minus. The sum of these two is referred as the free available residual chlorine. So the residual chlorine word means that it is the chlorine available for disinfection. Apart from free chlorine, we can also have chlorine in combined form. That is, we can have when there is ammonia present or organic nitrogen compounds present, we can have reaction with HOCl where it leads to monochloramine, dichloramine, nitrogen trichloride as shown in the reactions here. These chloramines also have some germicidal action, but they are not as effective and also they are more slow acting. The monochloramine and dichloramine have important action which is related to disinfection. So the levels of these of course vary with the pH, temperature, the contact time provided and the HOCl concentration. These are your combined chlorine residual, the NH2Cl which is monochloramine and NHCl2 which is dichloramine. Okay. However, first when we add chlorine to water, chlorine would first go to react with all reduced organic and inorganic substances such as Fe2+, Mn2+, nitrite, H2S, other organic compounds, and all of this would react with chlorine, okay. That imposes a chlorine demand. So only after this chlorine demand is satisfied will the chlorine added to water act on the pathogens. That is why the residual chlorine increase will actually be effective only after the chlorine demand has been satisfied. Now you see here how the actual residual chlorine varies with the chlorine dose. So initially when I have added chlorine, between this region A and B, there is no increase in residual chlorine because the chlorine is being used for oxidizing reduced substances, either inorganic or organic. Subsequently, what is happening between B and C is that there is some combined residual getting generated due to the reaction of chlorine with organic nitrogen compounds. So we have combined residual generated, then there is some destruction of combined residual. It decreases due to that destruction process, and then some combined residual still remains at the point D. Point D is known as the break point. Beyond this point, as we add chlorine, we will have continuous increase in residual chlorine, that is the free residual chlorine. So at any point beyond the break point, I have some combined residual chlorine and some free residual chlorine. And this line here is parallel to the 45-degree line, okay. So you see, this curve is referred as the breakpoint chlorination curve. It is very important for determining what is the chlorine dose needed in a given water. Without this, I may add a fixed amount of chlorine and have no residual chlorine left, okay, or I may have only combined residual, which is undesirable. Now this breakpoint chlorination gives the variation of residual chlorine in water with increasing chlorine dose. This type of a curve is used both for water and wastewater to understand how much chlorine dose should be added to the water. So depending on the water quality, we have to add sufficient dose of chlorine. We may have to add more chlorine when there is more reduced substances in the water, okay. So we have to tailor the dose of chlorine that is to be added by doing a test like this. So for good chlorination, I have to ensure that I have chlorine dose beyond the breakpoint dose. Now let's highlight that this bactericidal or the germicidal action of chlorine, how it varies for the different species. So what does chlorine do? Chlorine actually has a high oxidation potential, right? So it can oxidize the bacterial cells, it can oxidize the protein coat of viruses. So it has a ability to destroy the structure, to destroy their function, such as respiration. It destroys the bacterial enzymes and nucleic acids. And with all of these, it can kill the pathogens. Protozoan cysts and viruses are much more resistant to chlorine than the bacteria, okay. So protozoan cysts and enteroviruses are more resistant to chlorine. Now the rate of disinfection using chlorine varies with a lot of things. It depends upon the concentration, it depends upon the contact time, the form in which the chlorine is available, which itself is a function of pH, and it also depends on temperature. Higher the temperature, higher is the effectiveness of kill. Also among the various species that I mentioned, HOCl, which is hypochlorous acid, is more effective in disinfection. It is 40 to 80% more effective compared to OCl minus. HOCl can even kill viruses. OCl minus is less effective. OCl minus is your hypochlorite ion. It is much less effective than HOCl. As the pH increases, you have more of OCl minus. As the pH at lower pH, you have more of HOCl. So the chloramines also have some disinfection power, as I told you, but their disinfection power is even lower than OCl minus. So free chlorine residual is more effective for disinfection compared to combined chlorine, but chloramines are more persistent, and that is why in the distribution system we do want some residual in the form of chloramines, because they can persist longer than the HOCl and OCl minus. So combined residual is desirable in disinfection. So it will protect the drinking water from getting contaminated while it is moving in the distribution system, and it can also control the growth of algae, bacteria, etc. So that is why combined chlorine residual is also desirable. Now some of the problems with chlorine, using chlorine for disinfection is that it causes generation of trihalomethanes and other disinfection byproducts. These disinfection byproducts can have various effects. For example, trihalomethanes is like chloroform, chloroform or bromochloroform, all the combinations. Think of methane where the H is substituted by 3 chlorines or 2 bromine and 1 chlorine. So this way you have trihalomethanes. These are all carcinogenic, and that is a cause for concern. So the disinfection typically follows up a Chick's law sort of rule. So if n is the number concentration of microbes, dn dt would be equal to minus kn. Okay, so it's a first order decay. That is what Chick's law is about. Modified Chick's law is where it is minus k times t to the power m. Okay, this is a modified Chick's law. So m can be equal to 1, that is Chick's law. M less than 1 means the rate of kill decreases with time, and m greater than 1, that is rate of kill increases with time. All of these are possible. Now, depending on the residual chlorine concentration, we will have the disinfection is going to be affected. Okay. So, what I mean is the concentration of microbes remaining is always a function of what you started with. So, n by n naught can be given as a function of Ct. This is just an example. For example, I may have this expression where n by n naught is a function of Ct. C is the concentration of residual chlorine, T is the contact time. C and T together determines what is my decrease in concentration of organisms. Now imagine, given a chlorine dose and given a certain time, it is very important that we have low n naught to start with, because if my n naught is high, then my final n will remain high. I want negligible coliform count in drinking water, right? It should not be present. So, to ensure complete disinfection happens, I should choose source water which has a low concentration of microorganisms. So, disinfection of water containing natural organic matter with chlorine is of concern because chlorine reacts with NOM to generate disinfection byproducts such as trihalomethanes, which are of carcinogenic concern. Now, apart from chlorine, I would like to highlight that there are other processes in the treatment train that also causes removal of pathogens, such as your coagulation, flocculation and settling process, the filtration process, and another process which I did not cover today, which is the softening process. This softening process uses, such as the lime soda process. It is based on precipitation and it needs a high pH, and that high pH kills pathogens quite effectively. In coagulation, flocculation and settling, it is not a killing mechanism, but it is basically pathogens get removed with the sludge. In filtration, the filter backwash water would have pathogens in there, particularly pathogens like protozoan cysts. These are removed quite effectively through filtration. So, we do all of these upstream treatment to effectively remove turbidity and also remove pathogens together with turbidity. So, through the water treatment process, what are the things that we removed? We removed particulates and we removed pathogens, right? And also color causing macromolecules. Other things, if I had low molecular weight organics in there, the treatment train that I used, which is the traditional treatment train, cannot remove them. Okay? So, it is important to realize that it is primarily targeting the removal of particulates and the removal of pathogens. Again, note that particulate removal is done before the specific disinfection process, which is targeted to remove pathogen, because while removing the particulates, we are also removing quite a few of the pathogens in the process. Moreover, if particulates were present when I was trying to disinfect, the disinfection process will not be effective due to the shielding effect of particulates. Pathogens will not get disinfected as effectively. I would like to end this on this note. Thank you.